Good morning again. Thank you very much for being here with us today. My name is David Dopico. I'm the Business Development Manager here at Anyverse, and we're gonna introduce you today our solution for the in-cabin monitoring systems. At the end of this webinar, we're gonna have a slot to have questions and answers. So please, if you have any questions during the presentation, just send me the question and I will hold it until the end and we will give you all the answers that you want. With us today, it's gonna be Javier Salado. It's our technical product manager, and he is the person in charge of the strategic and definition of the platform and the product. He's normally doing the prospecting and working with the hand by hand with our customers to understand their needs and implement the solution for them in our platform. So Javier, please go on.
Hello, everyone. Thank you, David, for the introduction. And thank you, everyone, for attending the webinar today. I hope you find the content that we're going to share with you today interesting. In summary, we're going to be looking at the in-cabin monitoring regulation around the world. So what is the law enforcement doing to promote this in-cabin monitoring? What are the monitoring use cases that derive from these regulations? What are the data challenges to produce the necessary data for the monitoring systems to actually learn what to understand inside the cabin of a car? And finally, and the bulk of the presentation will be showing you the Anyverse synthetic data generation platform and how you tackle with it the generation of data. Finally, as David said, we're going to have a Q&A turn. So please place your questions in the Q&A panel, and we'll make sure that everyone gets their answers. So with any further ado, let's start with the regulation. I'm going to start with the European regulation. This regulation comes from this roadmap that you see on the screen is the 2020-2025 Euro NCAP roadmap for safety measures in new cars. This roadmap was depicted in September 2017, and it describes different safety measures that the new cars should have and the different milestones that those measures are going to be having during the lifetime from definition until they're implemented in new cars. As you can see, there are two of these safety measures, driving monitoring and child presence detection, that involve some kind of system that is monitoring the inside of the car, mainly for looking at the driver and looking for children that may be unattended. The milestones for these two systems are a little different. For the driver, the milestones starts in 2020, last year, and there will be some new milestones in 2022, and the last one will be in 2024. Whereas for the child presence detection, the only milestone and the principal one will be that the cars need some kind of system to detect this in 2022. So in order to implement this roadmap, some regulation and legislation is needed. So in November 2019, the European Parliament basically approved this regulation to first define what it is driver monitoring. And basically it focuses in three aspects: driver drowsiness and attention. And the first milestone for this is next year in July 2022. So meaning that a minimum of some drowsiness and attention warning has to be implemented in the cars. The second one will be the advanced driver distraction. This goes beyond not holding the steering wheel with two hands or looking at things that are outside the road or the rear view mirrors, and things like that. All the distractions with holding things in your hands and stuff like that. And the third one will be the availability, driver availability monitoring. This one is specific for semi-automatic vehicles, the ones that have some kind of level 3+ or 4 capabilities, to make sure that the driver is available and ready to take over any automated system that may be at some level driving the car. And in May this year, the assessment protocol for the child detection was published. So this has to be enforced in 2022. And child detection basically is make sure that no children is left behind unattended inside a car. In the US, things are a little different. They're a little bit more relaxed. It's a less regulatory space. But anyway, in November this year, with the big over $1 trillion million Infrastructure Investment and Jobs Act, there was a part that is dedicated to driver distraction, so driver monitoring in terms of driver distraction, disengagement, automation complacency by drivers when drivers are using automated systems, if they are attendant to what that system is doing or not, and foreseeable misuse of advanced driver assist systems. In terms of child detection, there was a 2019 Hot Cars Act that was included in the Infrastructure and Investment Jobs Act that took care of legislating to make sure that the new cars will have some kind of children detection. And independently of what the US Congress has passed with these bills, by the way, this bill was passed by the House in 2021, and President Biden actually signed it off in November this year. So besides Congress, the Alliance for Automotive Innovation has committed to add some rear seat reminder systems in new vehicles in 2025. So this is basically an industry conglomerate of companies that have got together for some commitments, but there is no legislative bond to this. And then the National Highway Traffic Safety Administration basically is the counterpart in the US of the Euro NCAP, has a driver distraction program that basically measures systems that may be in the cars that are monitoring the distraction of the driver, which is compliant with the legislation that has been passed today. We will be sharing the presentation, and you have the links to the details of all these laws and regulations. And finally, there are some pan-European and multilateral efforts besides the European Commission and European Parliament through the United Nations Economic Commission for Europe to add some regulations regarding the driver monitoring, basically driver presence, availability, and attentiveness. So basically, this regulation has a definition on what does it mean presence, availability, and attentiveness. So based on all these regulations and bills and initiatives by the private sector to regulate the safety of the cars, there are several different use cases that could help us to define the systems that will implement all those regulations. In terms of driver monitoring, the use cases or the systems that we may define and assign have to do with gaze detection to make sure that the driver is looking at the road, the rear view mirrors, or if it's losing attention just by moving the head. We're going to need body pose detection as well, how they're using their hands. So that's another system that we may put in place. Drowsiness detection, which is related as well with the gaze and the pose, because there are very specific poses that may yield to the side that the driver is drowsy. There are other initiatives to monitor other health parameters with a camera, which is interesting, and that will yield to more sophisticated systems. Then we have object detection that may help to detect the attention of the driver. If the driver is holding something in his or her hand, may cause an alarm to go off. And for the child detection, we want to make sure that our systems are able to distinguish between different children, and the child seat detection as well. If the children are in the child seat, if the belts are on, if they're completely secure there, et cetera, et cetera. And overall, if there is a child alone in the car, that is a very specific case that needs to be detected. And on top of this, you can have other systems. Once you already have some cameras inside the cabin that are feeding images to these deep learning models that are implemented the perception system to monitor the driver and monitor the children, you can have other use cases like seatbelt detection, if everybody has the seatbelts on or not. Although there are already systems that do that, we can have the same system using the cameras to implement all those systems, so you don't have redundancy of different systems in the car. Pet detection, all the type of objects that you don't want to leave behind, for example, in the car at plain view and things like that. So the interesting part is that for all these use cases, the perception system behind it is most probably going to be based in deep learning models. And these deep learning models need big amounts of data to be trained and to perform well in the problem that we are giving them to solve, to detect certain things about the driver, children, etc. And for the different use cases, you may need completely different sets of data. And that yields to the data challenges that all these in-cabin systems have. The first one is that the real data for in-cabin monitoring systems is very hard to produce. Imagine that you need thousands and thousands of different images for the different use cases. If you need real images, you need to have cars with the cameras set there and recording continuously the behavior and what's happening inside the car. The first big hurdle for this are the privacy issues. In Europe, for example, every system that uses personal information and an image of a person is very personal, needs to be compliant with the GDPR. And that means that you can take those pictures, but once you process them, you have to destroy them. Or if you're going to store them, it's got to be with all the GDPR in place. So it's got to be secured. It's you have to have the consent of everyone, et cetera, et cetera, et cetera. So it makes it very difficult. And when we're talking about children, it's even harder because the protection it's even stronger for children. And besides that, even if you could have all these pictures taken, are you sure that you're going to have enough to train your systems to perform to the level that these systems require? Do you have enough variability? Do you have enough car interiors that your system can recognize? Different times of day, occupant distribution. If you are generating and producing the data yourself, you need lots of different actors playing the role of being in the car and doing different things. Are you going to have enough variability? And even depending on the use case, the variability may be completely different, like different types of objects that you need, et cetera, et cetera. And the lack of variability at the end of the day may yield to a bias in your system. And when we're talking about people, bias in gender, age, and ethnicity may happen. And for car manufacturers or perception system, in-cabin monitoring system developers that want to be global, they have to take this into account. Like the ethnicity of people is not the same in India than in China or in the US or in Europe. So all these things have to be taken into account. Now, what can Anyverse do to overcome these challenges? Well, Anyverse has developed a data generation platform based on a hyperspectral render. And the first part of the cycle to train a perception system, in particular an in-cabin monitoring system, it's to create a scene where you're going to be placing the objects of interest that your perception system needs to detect or recognize, and apply enough variability to that scenario so you can generate thousands of images, so you can train and validate your system. So the first part is what we call Anyverse Studio, and we're going to see it in a minute. The second is to have a render engine that can produce images as close as possible to the images that the perception system is going to be consuming when it's already mounted and functioning in the car. And to do that, you need spectral information of the scene that is being rendered that we generated with Anyverse Studio. And to do that, the render has to have the capability of tracing rays and saving all the spectral information of the light that is bouncing around in the scene until it reaches the sensor. And if you keep track of all that spectral info, you can simulate the sensor very faithfully. And that's the third thing that our platform does. You can simulate different counter sensors based on this spectral information that we generate with the render from the scene. The fourth is that you need to generate thousands and thousands of images, and you have to do this at scale. To do that, Anyverse platform leverages the cloud and allows us to applying the variability that you have defined in Anyverse Studio in the scene, have hundreds or thousands of different CPUs and GPUs in parallel using our render generating images. Along with the images, we generate all the ground truth information that the different models, the deep learning models, may need to understand during training. After you do that, after you train and validate your system with the data, you can evaluate the major KPIs of those systems, performance KPIs like precision and recall, and make decisions about a new data set that you may need to overcome some bias that your system may have. Imagine that, well, you didn't, your system didn't learn enough about how to detect children in the rear seat, that it's right behind the driver. Well, you can generate new images with Studio and go around the cycle again. So that's in a nutshell what Anyverse, the Anyverse platform do. And today I'm going to show you on the platform itself, how can we set up a scene for an in-cabin monitoring system? How do we apply the variability, how we generate, and what the results are. So this is Anyverse Studio. Here we have different workspaces that I've used to work on things. I've one that is called in-cabin testing. And if I go to the workspace, I have this workspace already preloaded here. As you can see, a scene for in-cabin is very simple. It's a car that you can see here. And we've placed some cameras inside. This camera in particular is placed in the rear view mirror, in the one in the windshield. As you can see, one of the things that is necessary is to have variability of different cars. So we have different cars with different car interior colors and everything, and we can add more cars as we move along. We are doing it constantly. So that's the first part of the variability, to change the car in every single shot. Then we need to change the occupants. Who are the occupants in the car? For that, we have different characters. Let me find them. All right. All kinds of different characters that we may use. So we can place them along in the car, and then we need the environment, lighting conditions, time of day, different backgrounds, where we're going to be placing our car that will give different conditions inside the car. So your deep learning model is resilient to different ambient lights, different times of day, even night scenes when they're very dark. So that's the other part. Now, how do we actually generate all this variability? Well, with Anyverse, we have a Python interface that have full control in everything that you have set up in the scene. Okay, so in my simulation, I have my cameras, and I have my car, and I have my car with different characters already there that I can manipulate, and that I can manipulate manually, set up scene manually, and then go to the generator and generate one single shot to see what's going on here. Okay, but at the same time, we have a scripting interface that allows me to control everything in this scene. We have this pre-built in cabin library that will allow me to first get the possible cars that I want to use, select one of the cars. Then I want to set the ego in a camera locator inside the car, so I can place my camera anywhere I want. The ego is where I place the cameras, and then I can move this ego anywhere I want. I have two cameras defined here, but I'm gonna only be using one in every single shot. So I randomly will pick one of them to generate variability on the data set with different sensors, different cameras. But I can take two pictures, one with each camera at the same time. That shouldn't be a problem. We will just generate more images in every iteration. But it's completely up to you, and all this is programmable. So once you have that, you have the different conditions. If it's day or night, the different conditions outside, it's sunny, it's scattered clouds, it's covered. And we can program some probability to have different weights and variability in the data set. The bigger the images in the data set, more relevant these probabilities will be. So they will even out, and you will have a well-weighted data set. If these weights don't work for you, you just come here, change those weights, and run your data set again, maybe on less number of images to generate more of whatever is missing, but yeah, it'll work perfectly. Then you set a background, like a background. So we have something behind the car. And finally, the same, some probabilities on the different occupation of the car. If I want only driver or only child, or I want the car empty, or I want a normal distribution, that means that a driver and some occupants. It could be 1 to 3 different occupants. It could be children of different ages with child seat, without child seat, etc., etc., etc. Right? So when I execute this, let me dock it back here. So when I execute this, you can see that the first thing this script does is to remove everything that is in the scene, and now it starts populating it. And in this case, it left it empty. So it's an empty distribution, left the car empty. I can go again, and in this case, we have 2 people and 2 empty child seats. So every time I run this, I will have a completely different configuration. The passengers are picked randomly from the library. The cars are picked randomly from the library. You can enforce to get more of this or more of that. That depends on you. But basically, this library that we provide for encoding assures all the variability that you require. Now, I've been playing with this along just clicking play, 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 play. So I changed the different configurations. Now, how do you generate this in a data set? Well, you see here this onBegin iteration script. This script is exactly the same script that I have in the console. And this script, basically, it's going to play every time there is an iteration to generate the data set. So here is where I say, okay, how many images do I want in my data set? This account that I'm using for demos has a limit for 100, but per different accounts, you can have different limits. So I can do thousands and thousands in one single go if I want. And the only thing that I have to do is just go here and send it to a data set, an incoming data set, click OK, and this will automatically generate different configurations, send them to the cloud, and one different render engine will be rendering that particular scene. Okay, and I can do this with thousands of them in parallel, leveraging the cloud. So what's the result of all that? Here we have some samples of the images. Here we have the camera that it's using is the IMX 390. This is the other camera that is placed not exactly in the same place, but very close to it in the rear view mirror. And as you can see, different shots, different cameras, different configuration, different illumination, different time of day, different characters, children, no children, seatbelts on, seatbelts off. You can see that the poses change as well. And you can see that the seatbelts actually react to the different poses that the characters have. One single driver, one child in the back facing backwards. And that's one of the cases where you may think that you want your system to understand different angles from the car. And to do that, you can basically place the cameras anywhere you want. And if you want, you can place the cameras facing the front from the rear. And that could be helpful to identify the children that are in the back. As you can see, these are the same cameras, but placed in a different position. And the generation of this is exactly the same. The only thing is that we will take the pictures from where you have placed the cameras. Again, illumination is the same. You can see the sharp shadows that some illumination can create when it's dawn or at dusk. So the variability is completely assured. Something else that you can do with Anyverse is take advantage of the hyperspectral render and define different sensors and ISPs configurations for your cameras. So when you configure a camera sensor, you can configure all the physical parameters of the sensor itself, the pixel size, wall capacity, different types of noise, the color filter array, the quantum efficiency curves, exposure, etc. And along with the ISP configuration, the mosaicing, white balance, and the different transformation matrices from the different color spaces and the gamma, you can mimic exactly what a real camera would take. And playing with the camera sensor and all these parameters may allow you to have effects that will help your model to perform better. You have to take into consideration that ISPs, for example, all these mappings to the different color spaces, these are thought to generate pretty images when they're going to be displayed in a screen, or when they're going to be printed, or when they're going to be consumed by humans. But with deep learning computer vision, the one that is going to be consuming the image is not a human. It's a machine. It's an algorithm. It's a model. It's a neural network. So you can tweak the parameters in the sensor and the ISP, so you can help your neural network to perform better. And that is something that may be very key. So once you define the different sensors, you can apply them to the cameras. And when you apply them to the cameras, one thing that you can do is to generate a sensor sample. This will generate only the spectral information of the scene, and it will allow you, it will place it in these sensor samples here, and it will allow you to play with the parameters of the sensor. Now it's applying all these parameters to the raw image. There it is. Right now, the original and the new parameters is the same, but I can, let's, for example, reduce the exposure time. So you get a darker image. You can play with the color filter arrays and make it color. It's easier if I do it the other way around, because I have to fiddle with the color mapping here and the white balance. I have a color one here. It's the same one, but in color. Right? And I can fiddle around with the color filters, downsizing to none, apply, and basically I will probably get something very similar to what we just saw. It wasn't black and white. There you go. So you can play around. If you notice this little noise that the image have, that is because I haven't denoised it, because that takes longer, and to do it live, it doesn't take that long. It's like 30 seconds or so, but doing it live, it's a little annoying. So that's why I have here the denoised samples, so you can see that actually the pictures are pretty good. This is another example that I have in color. I'll go into it right now, and the noise versions of that. So that picture of the lady, it's it's a little different use case to monitor the driver only. Typically, this is when you place a camera right on the steering wheel column and point into the driver, so you can very closely see what the driver is doing. Typically, these cameras are near infrared. Anyverse is hyperspectral, and today we're supporting the visual part of the spectrum. We're working right now on near infrared. The technology is ready. We just need information about the materials and the reflectance of those materials in that part of the spectrum, the near infrared, about the 780 nanometers up to 1000 nanometers or so, to be able to simulate the behavior of that, of those wavelengths when it bounces in the scene, touching different materials. For example, sunglasses are transparent for near infrared, and not for visible part of the spectrum. That's why you don't see the eyes in the visible, but you can see the eyes when you are illuminating with infrared. And that's something that we're working on. But in the meantime, until we have the full support of near infrared, there are some tricks that you can do with the sensor simulation to simulate the near infrared. You can see that this lady, it's a little illuminated. That is because I've placed, to generate this sample, I've placed a light pointing to the face in a very narrow cone, simulating the typical LED that you have in infrared cameras that is emitting in the 90, 80 nanometers or so infrared. That illuminates for the infrared, and then the sensor that supports the infrared will capture an image with taking into consideration the infrared. That is the outcome of that. It's a like a black, very bright black and white image where the materials that are transparent for the infrared will disappear, and the ones that are opaque will be bright in white. So we can simulate a little bit this by applying the all clear color filter array and non-demosaicing and what we saw before. And the result of that is this image, which if you take side by side this image with something that's been taken with a near infrared camera of the same scene, will be very similar. I'm not going to say it's the same because it's not, but it will be very similar. And for early stages in training, or to do some transfer learning training to already train networks with color and get them to understand near infrared feeds when they're in production. A data set made out of this type of images could actually be very useful. So basically with that, I think I've covered everything I wanted. I've gone a little bit above the assigned time because we wanted to leave some room for questions. So I'm all yours.
Okay, Javier, thank you very much. Let's start with the questions and answers. I'm going to start with some questions that we had in the chat. First one is, how do you generate the reflectance of the occupants? Do you use one smooth BDRF across the entire face, or does a face show varying BDRF as a function of location on the face?
That's a great question. I'm not sure. It depends on the texture that and the texture maps that we have on the skin. I have to check on that to see the BDRF function is uniform or it's location based. I'm making note of that because I don't have that answer. And please leave your name for with the bid.
Yeah, I have the name, no problem.
Okay,
We will send him an email later with the answer. Well, later, probably another tomorrow with the answer. So the next question is, how do you generate occupants? Do you have to do motion capture for for each one, or do you have models for the 3D grid and things like the seatbelt location?
Right. No, good question. We don't do motion capture. These characters that we have in our library come from two different sources. Either we have created them ourselves, our 3D staff has created the characters, or we have purchased them from different 3D providers. I mean, if you go out there, there are hundreds, literally hundreds, if not thousands of 3D artists that sell their work. And for characters, we tend to use providers. So what we require from these providers is that these 3D assets are rigged, meaning that they have bones and joints defined within the 3D model. And so on top of that, what we do is we apply animations. Those animations are generated by us, by our 3D artists, and they're available actually in the, let me show you, in the workspace here. What's this? So we have different animations like a pose for driving. So when you apply this to the characters, let me get a character here. You can see that you have the animation configuration. So this one has driving animation on, and no arms or head. Oh, it's got a face turn right 90 degrees animation as well. So then you have the weight, meaning that one will be 90 degrees to the right in this case. 0 will be nothing, and everything in between. So you can control all this. You can assign some arms stretched to the different arms and different limbs. So anything that it's in the animations, and then apply again the weight to it. And all this can be done programmatically. So when in the library, in this script, we pick a character, we place a character, these functions here that will, where are the functions? This one, normal occupant distribution. Basically, this function is picking characters, placing them in the different places, and applying different animations randomly to them. So you can generate different, several different poses.
Okay, thank you. And I got here the last question I got. It's what type of render technology are you using to achieve these results?
Right. Yeah. Well, I mentioned it during the presentation. We use a hyperspectral render. This is our own technology. Anyverse comes from a mother company called Next Limit that has over 20 years experience in computer graphics and has developed the Maxwell render and other simulation software for computer graphics like RealFlow that's been used extensively for special effects in movies that you have probably seen. We have leveraged all this technology to create the Anyverse render. I think it's the only one that I know that has full hyperspectral information when it renders any of the scenes that you define. And that capability alone gives all the flexibility that I hope I have been able to show you today.
Okay, thank you. I have the last question here. Let me see. So do I understand correctly that you get 3D models and textures from house and outsource, from in the house and outsource, and then you overlay BDRF and animation?
Exactly.
Okay.
Yeah. When we get 3D models, not only people, characters, but the cars and any other asset that we have in the library. We need to post-process them so they can be used with our render to get all the hyperspectral information. And that is, of course, looking into the materials, applying the VDRFs, et cetera, et cetera.
Okay, fantastic. So I think that with this we can basically end this webinar. I will appreciate if you can follow us in LinkedIn. Our LinkedIn page will have all the updates of our technology and every single webinar or event that we're gonna make. Also, you have here different channels where you can contact us. If you have any questions, we will be more than happy to answer them. Also, I would like to remind you that now you are gonna get a quick questionnaire to give us a feedback about the webinar and how did you enjoy the webinar, if there is any other topics or any other kind of use cases that would you like to talk about in another webinars. Please just give us the feedback and we will be more than happy to improve our webinars and our different events for the next time. Just thank you very much for being here with us today. You will get an email also with the video of this webinar for you to watch it later if you want. And I hope you enjoyed and have a great day.
Thank you very much, everyone. Thank you, David, and thank you everyone for joining us today. Bye-bye.